All right, we're going to get this going. Let's get this kick-started. First of all, most important thing, thank you all for coming out to be at the last session of the day before the party. It's definitely not lost on us that we're between everyone here and getting through the party or grabbing a beverage or doing whatever it is to decompress at the end of the day. This is service integration, delivery, and automation using Amazon ECS. So we're going to talk about a couple things. We're going to talk about what's going on with different things around just container deployments, things that Here has learned actually as well. We're going to bring up the Here folks. I've worked with them now for pretty much the larger part of this year. And I've learned a lot about what they've been building, and they're going to come up and talk to you about it. So you should expect to see a lot about different types of services that are being deployed along with ECS inside of containers. We're going to show you some of those. I'm going to give you a quick little overview of some popular ones, Apache Foundation services that have interesting dependencies. And then, like I said, Here's going to come up and do an overview of their open delivery platform, and they're going to talk about their practices, their open location platform, sorry, and their delivery practices that they've actually learned over a couple of years. And then some best practices. The guys were talking to me a little earlier, they really don't want anybody else to make some of the painful, arduous mistakes that they kind of went through early on. So best practices are often relative, and also complexity, right, is often relative. Like what you consider to be easy or hard is sort of a basis of your experience. So some of this stuff we would consider obvious things that you need to be thinking about. And for some of you, maybe you're just getting into containerized deployments, and it feels like this is pretty deep and advanced. If you have questions, we'll have some time hopefully at the end, or you can hang out after and talk to us. The ecosystem is moving fast. So these things do continue to evolve. They continue to change. So you do have to keep coming back and learning more, right? I think that's probably one of the biggest lessons as I joined AWS 2.5 years ago. Like this is a learning job. Like everything is about what's coming, what's new, what value does it add, and that's a key. And last, kind of a follow-on to that, these things are not frozen in time. All right, PSA, public service announcement, as it relates to DevOps. I won't read this out to you. I'll let everybody kind of get through it. At least a few chuckles before I try to move on. Right? Agility, speed, thinking about things in containers is a big part of that journey for a lot of customers right now. So on its face, containerization, thinking of a layer of abstraction, looking for all the benefits of portability, looking for speed to launch, all the things that you hear about with containers sounds sort of relatively simple, kind of obvious. But then it creeps a little bit, right? There's a bit of a leaky abstraction problem. You start seeing configuration of the types of services that you're deploying being a challenge, right? All the stuff that runs inside of the container still needs to be managed and operated at scale. And potentially, you're going to deal with a lot of challenges as you start to get these things moving and start dealing with different types of complex systems that have dependencies. Service discovery, common issue that you hear about. How do I register something that's available and can be found, and then I can actually sort of move those things around? Because the idea of containers is that things are very dynamic, right? Stuff's kind of popping around, popping in, popping out, adding stuff. So how are those things, how are they found? How does stuff get removed? How do I not start routing to ports that are no longer existent? So the volume, the scalability, HA challenges, these are the things that start to kind of show up when you try to productionalize what's going on with your containerization deployments. And that's where I think the lessons you're going to hear from here are going to be very, very helpful. So not everybody is super familiar with all of these Apache Foundation services. So I'll take a quick minute or so to explain what each one of them are. Kafka, it's a service for a piece of software for doing streaming software, streaming solutions. So bringing in, those massive amounts of data, ingesting massive amounts of data, and you'll see very much why that's a critical component to the Here solutions. It takes a dependency on Zookeeper, and you were probably going to notice a theme here. A lot of things take dependencies on Zookeeper, right? And Zookeeper in its own right has complexity, right? It's got HA challenges. It's got latency sensitivity. And that can be sort of your Achilles heel if that isn't operated and managed well. And then Storm. And Storm has a lot of continuity as far as taking and building out topologies and spouts that can find the incoming data that's through Kafka. And these three work together to give you solutions. And when you start to take these and put them into a containerized deployment, you've added a layer in between what these are looking for to operate. And you have to figure out kind of what are the best mechanics for dealing with that inside of containers. And then you think about ECS. Service discovery. Let's baseline on this real quick. And the first thing I'll say is, right, finding services. We kind of have a solution for that, don't we? Isn't it DNS? DNS is a bit of a dated kind of a solution, and it obviously has latency challenges, refresh challenges. Remember what I said a couple minutes ago. It's dynamic. Things are changing rapidly. I can't deal with some of these kinds of challenges that DNS brings to the table. So I need a solution for this. And I need a way to register. I need a way to check on health. I need a way to go across different service boundaries. So containers sort of have not introduced this challenge. Service discovery is certainly still relevant outside of containerized deployments, but it certainly has amplified the need. And now you see this as a pretty early phase necessity for customers that are going to production with container deployments. So how would you do this on AWS? And I will qualify this and tell you that there's a few things that make it possible. But this is really if you're just getting started and you're looking for a solution to get out there and start looking for, in a closed system, right? We've got Route 53. It's a closed system DNS solution that you can control, right? So it's not a wrong model to leverage that for service discovery, but there's a bit of a distribution kind of challenge there in that you've got to figure out how to manage it. Now we've published some things. You can go out and find them online. There's ways that you can use CloudWatch and Lambda to sort of register and unregister events. And I want to show you there's a Go agent that was written and published out to GitHub not long ago that one of my colleagues has worked on that'll actually look at the Docker events and be able to register or unregister services inside of a registry, right? Now, what about health checks, right? There's other things that you still may be looking for, and there might be, other benefits that I'll let the here folks tell you about, because there's solutions from HashiCorp Console, for example, that they're going to talk about that give you a centralized model and potentially a little more advantages as you start to scale. This is some code. Light gray on a white background might have been a poor choice. Hopefully everybody can see it. The key thing you're seeing there is the endpoint at the top is listening in on the incoming events, the Docker events, and then this function is able to execute. This function is basically going to call the APIs against Route 53 to register and unregister things, right? So this is able to do an effective job of getting those services out of rotation when you're looking for that service discovery solution kind of in the early phases. Last but not least, this is my last slide, another factor, and this kind of comes into the centralization versus using separate services discussion. Configuration data, also a big challenge. Mentioned that configuration is part of what makes these things hard. How do I get least privileged mode access into configuration data in AWS? Well, you get that with IAM roles, right? We've had the ability to do EC2 roles and be able to do that at the host level. Well, but then you got to think about it with containers, because now we're trying to densely pack containers into hosts. And fortunately, the ECS team has brought on IAM roles for tasks. So now you can get the granularity that you're looking for. You can get that kind of access privilege management, and you can go ahead and pull the configuration data in. There's other advantages. We do have things like S3 endpoints. So if you're storing your configuration in S3, you can start to lock down the routes to that data. Again, mind you, this is the idea of how would I start to pull this stuff together if I was going to use just exclusively AWS services to do this. So all the goodness is still there, rotated credentials, the things that where the metadata service is called back, and that's how you've done security across EC2 to other things in AWS for a long time. Okay, so that's kind of the introduction. Now what I want to do is I want to bring up Pascal Hahn, the director of cloud architecture at Here. He's going to talk about the open location platform and some of the work they've been doing.
I'm going to, the mic okay now? Okay. I'm going to start covering first what here actually does. So here's a location company. We've been in mapping for the last 2 decades, I think, at this point. I've not been with the company for quite that long, but I've been there for the open location platform from day one. What the target of the open location platform is to pull data from various different data producers, make it available to data consumers, and enable developers to really use that data. So what we're doing with automotive, which is the first customer base we're working with right now, and also coincidentally our owners, is that we're taking in data from vehicles and we make it available across different manufacturers. So we're a third party. We take in the sensor data and we then create location experience. So be that predicting the time that you can arrive with a car, be that improving traffic data, be that figuring out that, hey, there's like a dangerous situation on the road and making others aware of it. So to do that, like every data that comes from a vehicle is always geospatially bound. So what this means is all these sensors, without actually knowing the location of them, they don't give you any value. If you're a location company, you have a lot of experience with making sure that sensors are actually placed on the map correctly, that you can do the geospatial operations you need to. And that's really where here comes in and why we're having this very targeted analytics platform for this domain. So there's 4 phases of all the experiences we're creating. So the very first one that I just talked about is the ingestion. So if you have millions of vehicles and you need to get the data into a giant data pool, this brings scaling challenges. So as Tom said, Kafka is one of the components we're using as a data transport here. We learned a lot about scaling Kafka, but I'm not going to go into that in this talk. Once it comes in, you need to enrich the data. So it's nice to have a sensor with a GPS coordinate, but how much does that actually help you? Like what people actually need in this case is like, hey, what link of the road is this on? Is this a highway? Is this not a highway? Is this like maybe during like a rainy phase or during a different weather? Like really the metadata you can add to this sensor data that is geospatial data, in a lot of cases data that we already have, is what people start getting a lot of value out of when they jump to the next step. Like you want to process all that sensor data. So when a customer has the data pooled across multiple manufacturers and they actually want to start running an aggregation job, like they rely on the map data to be consistent across all manufacturers, which from experience I can tell you when we take the data in, that's not always the case. I'm going to jump into processing quite a bit and how we do that part, and that's also going to be a bit of the focus of the system itself in this talk. The last path is publishing. Like, yes, you have a map layer at some point that shows you all the traffic globally or wherever we got the sensor data from. If I try to pump all that data to every vehicle that is connected to this platform, we're going to break the bank in transport, and this is also not going to scale at all. So we have relatively smart publishing systems that are, again, geospatially enabled, that just replay the data to the cars that is actually required, and so on and so forth. To jump into the actual data processing, we have a tool called the Analytics Execution Environment. So what this does is enable people to really simply do analytics on data that they already uploaded to the platform. So this is things like, hey, I want to manage a bucket of data. Yes, you can do this in AWS with S3, but not everybody actually knows everything about permission management that is related to that, about data cleaning, about how you actually manage all this in detail and at scale. You might want to share that bucket with just a different user. So do you want to figure out how the IAM roles work? For somebody that just tries to do analytics, which most of the time is a data scientist, it's way too much. Then you want to manage processing clusters. You need to be able to look at the data that you have access to. You need to manage processing chains, which is like, if I get a new data set that comes in from a vehicle, I actually want to attach it to this processing chain that then can calculate, I don't know, how many vehicles drove on this road over the last day or two. And then you want to do user management. It's like you want to give access to your colleague to look at the cluster you have and to look at some of the data that you prepared for him. You might want to give him access to your data bucket. You might want to show him the experiences that you're currently iterating on. Then also operational services are a big thing here. Like if you run this and it becomes a security relevant system for automotive, you really want to make sure this is up and running, and not just from time to time, but actually reliably. So we're also dealing with monitoring, with like insight into cost that obviously is being created as you use the platform, the performance of everything, that the latency of the sensor changes where you expect it to be, and so on and so forth. At a very high level, the architecture we're talking about is really layered on top of a lot of different AWS services. And this is a very stripped down list of services that we're using. But if we go from bottom up, I just showed you a brief screenshot of the UI. The UI itself is built on a UI framework. So as our internal teams are starting to create different experiences in this UI, we kind of give them the ready-made building stones to just put it together easily so it looks consistently and it's also developed in the same way. To everybody's surprise, the UI framework sits on top of a REST API. I think this is a pattern everybody knows in and out. Underneath all of this, we have a service deployment API. So when it comes to creating a processing chain, when it comes to creating a batch cluster, when it comes to creating real-time chains, we have an API and a framework underneath that is doing all this deployment for us that wraps around things like ECS, as Jeremy is going to show in a little bit, S3, ELB, EMR, and so on and so forth. Also, we have a very strong user and authentication component in this. So as you can imagine, we can't have a situation where Audi suddenly would see BMW's data, to pick an example, by accident. And they could basically start loading their data. They could do whatever they want with it. If this is not intended, we really have to make sure this works properly. So we have a resource management API that actually federates here users into AWS. So we can take a here identity, we can give them the appropriate access in AWS, and we do that very seamlessly in an automated fashion. All that on top of IAM, obviously. With that, I'm going to let Jeremy really take a look on how does here actually deliver these services. As you can imagine, this is a multitude of microservices that this is all built out of, and there's a lot of complexity to actually managing this platform at scale, and Jeremy is going to give you a deep dive on that.
Hi, my name is Jeremy Brown, and I'm a lead engineer at Here, working on service delivery and orchestration of service delivery. Let's see. I think my notes will come through better here. As Pascal was telling you, at Here we run a complicated microservices architecture to perform data processing and service delivery. This includes deploying already hundreds and potentially thousands of Docker containers, and all to AWS. We want to share several high-level principles and strategies that we discovered that make dealing with this kind of scale reasonable. As you can imagine, we learned a lot of lessons on the way. We made some small mistakes. Some of the small mistakes that we made led to big headaches, and we'd like to be able to share some simple strategies to help you guys avoid some of that headache. At the core, there's really nothing overly complicated about these strategies, and that's actually why we like them and we wanted to share them with the group, because they're relatively easy to implement and reason about. I suspect that most of you have worked on systems that ended up becoming a lot more complicated than they had to be, and that the situation was frustrating, slow, and impeded your development. So I hope you can use some of these strategies to avoid the frustration. Here you see an architectural diagram of our service delivery. So at Here we created this service delivery architecture to simplify and automate and organize our deployments. We wrote a simple tool called Canon or standard tool called Canon to automate deploy strategies. It runs the deployment, update, and undeployment of containers to AWS, and it automates configuration and secrets changes. One really important aspect of deployment tooling is the idea of idempotency. That means if a deploy runs 1 or 2 or 3 or 4 times with the same configurations and container versions, the deployment's not changed. It just updates the state to whatever the application configuration was set to. It doesn't go ahead and deploy a whole bunch of extra stuff that you didn't want. We also wrote a pretty simple tool called Optic to update the parent image tags in Docker files. This was so that in CI/CD we could easily promote updates of base containers and trigger builds. Most of our containers are deployed now to ECS clusters in a standard AWS VPC capable of holding like 1,000 hosts. Inside the VPC, we run a HashiCorp cluster with Consul and Vault, and in our made production cluster, we run an S3 back Docker registry. One really important aspect is that all of the environments are production-like. The only thing that changes between the cluster is configurations that are stored and the role, and they're just in different AWS regions, and they have dev and prod roles. We run different clusters for dev and prod, and we run different clusters for different portfolios. Right now, we run about 20 of these. None of them are completely full, but this is potentially a lot of services to basically manage. So Tom earlier, he outlined some of the importance of service discovery. And this is a critical component when running a lot of microservices. So first, I want to do a little bit more detailed talk about Consul and Vault. Consul is a distributed and highly available service registry. Whenever we have a container that comes up in our environment, it registers itself to Consul and makes itself available to other applications that would like to integrate with it. This is really important because in our system, normally you think about a service to a node as being a one-to-one relationship. And really, in our system, a service to a node is a many-to-many relationship. So each node runs many services, and each service potentially runs on many nodes for HA purposes. The service discovery also includes DNS, so you can just do standard DNS discovery, and this is very good when you're doing things like forwarding from an ELB to a service. It also includes KV storage. We store almost all of our immutable configuration in the KV store. This is really valuable because you can go to the KV store, you can easily update any configuration, and tooling that we have right in the container will update a templated file with a new configuration and restart the service. And I can literally change configuration in a web UI. I can see my changes right in the application. I was literally using this earlier today to troubleshoot some configuration problems we were having with the deployment. It just makes it really easy to troubleshoot things. And then most importantly, health checks. So because we have many versions of a service, or we have many copies of a service running on many nodes, we want to be able to have round-robin DNS. If a node goes unhealthy in an HA fashion, we want to stop routing traffic to it. And if we have a health check that can fail, the health checks are highly configurable, and you can just take a node out of service. We can fire an alert into our NOC, and a technician can go and try to troubleshoot the problem. Meanwhile, most users don't even know anything happened. And then there's Vault. We use Vault as a distributed HA secrets management tool. I don't think that I need to tell anyone the importance of security. It just provides an encrypted KV store. It works great with a templating mechanism. We use Consul template. There's some other tooling that you can use that works just as well. Vault is also really good at generating secrets and certificates, and also revoking those secrets and certificates and enforcing time to live on the certificates. I want to talk a little bit about service registration and discovery in detail. It's not only important to register services dynamically when they come up and go out of an environment, it's really important to organize them in a clean manner. We learned some lessons around this, and what we decided to finally do in the end was organize our services into namespaces and service name. So you can see an outline here. There's a typical Tomcat MySQL stack that we all know about. We could have multiple versions of the stack running. Team 1 and Team 2, as you can see, can have their own version of the stack. And the Tomcat can discover its MySQL by just looking in its own base namespace for the MySQL that's registered to that base namespace. We can store the configuration and the passwords for discrete deployments at these paths. It just works in a really nice fashion, just like a file system, to organize all of the services, and it makes it really easy to reason about. It makes it really easy to do pattern recognition and just find what you're looking for. So here we can see the similar set of applications just rendered out into a tree. And you can see how we land with like a nice, neat organization. And it's not difficult to find anything. Everything is easy to reason about, and it just kind of makes sense. This relates really nicely to policies and security. So here you can see an IAM policy that's been written out that basically allows ECS access on a specific cluster that's named after an application that runs in a namespace. So it ties up really nicely to the registered service name. And you don't have to do any kind of many-to-many or strange mappings between policies and what you're going to end up enforcing and where those policies are run and managed. Similarly, there's a console policy, so you can see the same idiom right here. Basically, we reinforce the private configuration for the node and its secrets on the private path. So a specific application that runs in the team1 dev app1 namespace is given write access, so it can read and write based on that path. And it's allowed to register itself to team1 dev app1, so nobody can come in and spoof the system and register themselves in a place that they don't belong. So we use this to basically make Zookeeper, Kafka, and Storm work really nicely with our deployments. We wanted to be able to deploy any number of Zookeeper, Kafka, and Storm stacks for our CI/CD purposes. We wanted a developer to be able to throw up their own copy and know exactly what was happening in their stack. So how this works is that first the Zookeeper containers start up and they register themselves to console. In this case is team1 dev app1 Zookeeper 1 through n. Usually we run 3 to 5 Zookeepers. And then they look for all of the other team1 dev app1 Zookeepers. And they can configure themselves. They can get the IP addresses that they need right out of console. And we can bootstrap the Zookeeper cluster, and it's up and going, and it's running in its own namespace. After that, we start up Kafka. It comes up, and it looks for its Zookeeper cluster in the same namespace. And then it registers its brokers as team1 dev app1 Kafka 1, 2, 3, 4. And it finds its Zookeeper clusters. Everyone's happy. And after that, Storm comes online, and it configures and spouts to listen to all of the topics on team1 dev app1 Kafka and all the queues that run there. So you can see how we can very quickly segregate teams, environments, separate applications in the environments. Everybody gets their own copy of the environment. Someone throws away their environment. They don't want it anymore. It doesn't affect anybody else. You automatically know what's being used and by who. Container management is also an extremely important thing when you're running a lot of microservices. So when configuring containers at runtime, we basically came across that there's a couple different strategies for how to do it. You can kind of gray things out and go sort of into the middle. The first strategy is basically completely configurable containers. And you see this strategy on the public Docker registry, where the containers are completely agnostic of the scheduler that they run on and how they get their configuration. It all just comes in via e-flags. This is great because it's really easy to reason about. The container is completely decoupled from the environment it runs in, and it puts all of the impetus of the basically the configuration right on the person who calls, or the scheduler that calls Docker run. On the other side, there's self-configuring containers, and this is when a container comes up and it uses a runtime templating mechanism and reads its config out of a key value store. It could be a database, it could be an S3 bucket, it can be whatever you want. We use console and vault. Container comes up and it reads its secrets right out of paths that are basically linked to its namespace that we talked about. The most important message, I think, to come across from this is to be very deliberate about how you choose your use case here. On the one hand, self-configuring or configurable containers are really easy to implement. The containers are immutable. They're easy to think about. Local development's easy because you just inject all the configuration in the run command. On the other hand, we realized that NVARs aren't a very secure way to inject secrets into a container. We didn't want to do that. Anytime you want to update a config on a container, it requires a complete restart of the container. And your scheduler also ends up being your configuration manager. So if you have a ton of configuration, it basically, Jenkins has to know about all the configuration, and it has to know about all the secrets. And Jenkins is not a very good place to store secrets, unfortunately, especially when they're injected as parameters into the Jenkins build and end up in NVARs in the container. Your secrets might not be safe. Self-configuring containers also have pros and cons as well. How we implement it, our base containers have code that basically retrieves the app configuration from console and vault. You could also use etcd. Keywiz is another secret store that you could use. There's also confd that you could use instead of console template if you wanted to. The pros of this, and I've seen the effects of it repeatedly, is that containers and processes can be updated on the fly. This is really nice for configuring Storm spouts and bolts at runtime if you want to, or Kafka queues. Nginx is also a great use case where we use this, where if you want to perform an update, you can literally write out a new Nginx config. You can do an Nginx reload, and all the new requests will take the new configuration, and you can implement connection draining right on Nginx just by rewriting a template and doing an Nginx reload. Secrets are stored pretty securely. It's an out-of-band process. It's not tightly linked to the deployment. They're kept in console. They're kept in vaults securely. And the configs can be easily viewed by the people who want to view them. You're not going into the Jenkins job and trying to figure out what job ran that deployed which container and what configurations were in that. You just go to the namespace in console or the namespace in vault. You look at what's in there. You can make a change. You can update it. And you can go check and see if your configuration change worked out. The downside of this is that it takes a lot more work up front to implement. Local development becomes a little bit more complex because basically you end up running console and vault on your dev machines. So it takes a little bit more time to get developers up to speed on how they're going to develop the containers. Another really important thing that we came across is how do we manage container releases and hierarchies at scale? So when you have many, many containers that are inheriting from many versions of another container, how do you make sure that everything's sensible and changes and updates of the base container, for example, for security, end up in the places that you need them without a tedious amount of manual work and tracking? This is where we came up with a simple tool called Optic. And it's only about 2,000 lines of code in Python. There's not a lot of complexity to it. Maybe we'll potentially try to let it out into the public someday, but I think just any senior, decent developer could implement this themselves relatively easily. The first thing that we do is we register our Docker images for updates. So you can see, like, for example, here, everything inherits from here CentOS 7, and here console and Docker registry and Java 8. They're all basically downstream containers. Tomcat, for example, is a downstream container of Java 8. And we just register them all in an XML file. And we have a tool that iterates over the XML file. It knows where to go look in the Git repo for the source code and find the Docker file for the application. Basically, we can iterate over this document, and we can go about, and we can look at the Docker files, and we can just discover the versions and the relationships that are in the Git repository. So you can see, for example, here, we've got from CentOS 7 in the Java 8. And then if you look in Tomcat, Tomcat's from Java 8, and we can see the versions that change. We can inspect the Docker registry, and we can find all of the versions, basically, that we pushed out to the registry. And easily, just doing some pattern matching on the Docker image tag, we can go ahead and we can find out what to update all of our Docker files to. So once that runs, we basically trigger a set of patch sets or a set of pull requests. If you use GitHub, we use Garrett, so we just have patch sets that we just inject into the code review system. And basically, someone comes along, they can accept the change. So here you can just see a sequence of diffs that were kicked off by a new version of CentOS 7, version 4. In the Java 8 Docker file, we upgrade it to the next version, Python the next version. That series of updates happens. Someone commits it into the repository, kicks off the CI/CD process, builds the new versions of CentOS 7, builds the new versions of Java 8 and Python and pushes those out to the Docker repository. And that triggers the next set of iterations where basically we update the upstream Java and the upstream Python into the downstream Tomcats and Flask applications. And at that point, the developers can just accept the review, and it just pumps back into the CI/CD process, and the layers of updates can kind of continue. Versioning is also very important. So each master verify build or each commit to master that we do results in a new Docker image that gets tagged as testing. So in our CI/CD process, we just use testing with a semantic version and a timestamp and a git rev so that we can always track back to the commit or the time of the build that any Docker container was basically tracked to. This also results in a nice, clean, natural order, and it just works out quite well. Once the Docker image passes all the acceptance tests, we just retag it as stable. And you can always pick the newest stable tag off the top of the stack, and you could update the next system and move forward from there. So this leads into the next topic, which is managing the service releases at scale. This all relates to how we go out and promote Docker containers. So you see the example for the Zookeeper Kafka Storm stack here. So once we have a collection of images that pass acceptance testing together, they get released by pushing a bill of materials out to an artifact repository. Now we can just take this bomb and we can use it to update any environment based on its own specific configs that are already stored in console and vault. We heavily rely on CI/CD to perform this process. So our CI/CD pipeline looks like a pre-submit verify. So when we have a pre-submit verify, for example, for like a Java application, we'll run all of the unit tests. If the tests against the jar, the built jar are fast, we'll build the jar and run some tests against that. But usually it's just unit tests that run, and it notifies the code review system. We use Garrett. Master verify runs whenever we merge a patch set to master. After that, we run all the unit tests again, and we build a Docker image. We run product acceptance tests on the Docker image. These are usually run in like natural language style testing like Cucumber. And this is to actually verify the build artifact locally against mock dependencies. So a lot of times we'll have jars that'll have mock dependencies like right in the jars that we can use for the PAT tests. Sometimes we'll just throw up simple mocks out of band, or we'll use other services run in mock mode. After we run the product acceptance test, we run a set of system acceptance tests. And these are feature-based tests. They run against the application that's deployed to the development environment like I showed in the earlier slide. All these environments are exactly the same as the production environments. The only thing that changes is the configuration and then the type of namespaces that we use inside them. We also run other tests on a case-by-case basis in these environments, product failure testing, product performance testing. Traffic forking testing is very important, so we'll use a tool called Gore that's right on GitHub to capture real-time traffic, and we'll throw it back against the new version of the application and see if performance has been affected. Once we have system acceptance test run, we have that bomb run, and then we can take that bomb file that I showed earlier, and we can push a version of the bomb out to a CIT environment. It's just another production-like environment that we run, and we allow customers to do integration and staging testing there. And then when that passes, we can push the same bomb file right out to production. So it just makes for a nice and tidy, easy to reason about system. Some statistics on speed of deployment. So we started using Docker before ECS was ready. So we had some of our custom tooling that used CloudFormation and Docker. And it worked fairly well for us, but it was kind of slow, and it was prone to some errors while we bootstrapped nodes and got them ready to basically run Docker containers. It took about 12 to 15 minutes to perform a deployment. We had about a 95% success rate because we would run into a lot of issues with the version of Docker changing, just all kinds of different things because we ran bootstrap code on the node via CloudFormation and user data. Once we switched over to ECS, our deployment success and iteration time went way down to about 30 to 60 seconds and a 99% success rate where failures are basically uncommon now. And that's what I have to share.